Welcome to this Ronin Institute public seminar. Our presenter is Immanuel Freedman. His topic is Modern Methods of Chaos and Babylonian Mathematical Astronomy. I have heard him talk informally about this topic. I think that you too will find his discussion informative and fascinating. I hope that you will consider engaging in discussion after his presentation. Immanuel Freedman, PhD, is a senior member of the Institute of Electrical and Electronic Engineers, a chartered physicist, and a member of the Institute of Physics. He received a doctorate in physics from the University of Durham, England. He is a multi-hyphenate leader in data science, systems, signals, and algorithms focused on imaging, modeling, and simulation in the pharmaceutical and telecommunications industries. Immanuel's contributions to the Institute of Electrical and Electronic Engineers, American Association of Pharmaceutical Scientists, and the International Society of Pharmacometrics include chairing scientific communities and serving on standards committees. As is customary, Ronin anticipates posting on YouTube a recording of this introduction and Immanuel's presentation. The discussion after his remarks will not appear on YouTube. Please feel free to look for this seminar and other Ronin public seminars on YouTube. Here is Dr. Immanuel Freedman.
Welcome to the Ronin seminar on Modern Methods of Chaos and Babylonian Mathematical Astronomy. I'm Immanuel Freedman, Ronin Research Scholar since 2020. This slide shows the learning objectives for this seminar. To understand the possible role of cultural contact between scribes and Pythagoreans, understand relations between music and Babylonian astronomy, explain the zodiacal distribution of Babylonian normal stars, understand relations between the mathematics of Babylonian astronomy and a modern chaos theory of nonlinear dynamics, apply mathematics of Babylonian astronomy to a modern problem. Our story begins with the excavation of Ashurbanipal's palace in Nineveh. As king of Assyria, a most powerful empire, he considered himself king of the world. Proud of his scribal training, unusual for kings, he could read and write his own messages and sent far and wide for books to add to his extensive library of cuneiform texts. This slide shows one of the astronomical texts found in the ruins of his palace. It is a table of predictions of the moon's astronomical position for the Seleucid era years corresponding to 104 to 101 BCE. This slide shows a part of the table, or ephemeris, that includes many columns with computation, quite similar to a modern spreadsheet. Some of the key sources for Babylonian astronomy are listed on this slide. Mulapin is an extensive compendium of astronomical knowledge that likely dates from the 11th century BC. Of particular importance are the records of astronomy, hydrology, commodity price, and unusual events curated over about 4 centuries with closely consistent protocol and data structure that are today known colloquially as the astronomical diaries. It is likely that these diaries form a substantial part of the Babylonian astronomical input in the form of inspected and approved diaries, and output in the form of almanacs, Golio texts, normal star almanacs, and tabular texts. Procedure texts document computational modules, that is, functions and programs, with headers, variables, and algorithms described by pseudocode. Modern research landmarks include the excavation of Ashurbanipal's palace by Henri Layard and Hormozd Razan in 1847 to 1849, the publication of astronomical cuneiform texts by Otto Neugebauer, who shared a corridor with Einstein at the Princeton Center for Advanced Studies, and sundry contributions for others, with a few scholars in each generation. The key challenge is that we have no information on record, save one, about how the scribes obtained their extensive sets of mathematical model parameters, and previous published analyses have been based on circular argument. How could the scribes have estimated their parameters from sparse, noisy observations over an extended period? Let's start with an understanding of the concept of resonance as expressed by musical scales. The question of the ideal musical scale and the concept of harmonious heavenly motion, divine harmony, were hotly debated in antiquity. The slide points out some landmarks in the development of ideal Pythagorean musical scales. Philolaus proposed that there is an unlimited continuum of pitches limited by intervals interacting according to a harmony, and identified the ideal octave, fifth and fourth. The remainder refers to the Pythagorean comma, which represents the musical interval between 3 perfect octaves and 5 perfect fifths. Archytas referred to the sound made by a stick whirling in the wind and pointed out that faster speed means higher pitch. He also noted that there was no mean proportional between numbers in superparticular ratio, that is, the first order resonances of the Pythagorean musical scale. Hence, the basic musical intervals cannot be divided in half in terms of rationals. Plato introduced the world soul in Timaeus, based on the listed intervals, while Kepler later noted a musical scale based on the planetary angular speed when closest to or furthest from the Sun. Resonances continue to play a considerable part in the modern theory of celestial mechanics, and in recent times the Nobel Prize winner Alfvén proposed a theory of planetary formation based on a jet stream of planetesimals that coalesce according to their resonances, that is, similar motions that reinforce each other. The so-called normal stars provided a fiducial reference system for Babylonian zodiacal position. While it has been generally appreciated that these stars form a rising time scheme for astronomical objects near the ecliptic, one of my contributions is to point out that their positions form a pair of musical progressions based on the perfect fifth and the Babylonian diatonic semitone. Let us note that musical harmonics are resonances. The picture shows the Queen's lyre reconstruction from Ur. It is likely that Sumerian and later Babylonian musicians and scribes would have learned that the strongest and most stable musical resonances have a superparticular ratio of string length and a small whole number denominator, a small divisor in modern terminology. The bull's head and blue-coloured beard suggest the Bull of Heaven, constellation of Taurus, with the Pleiades star cluster, whose heliacal rising signalled the contemporary vernal equinox. Consider the hypothesis that Babylonian planetary events are intended to represent well-defined states. This slide shows a conventional interpretation of the inner and outer events described by Babylonian planetary event models. B denotes the zodiacal longitude and T denotes time. The Babylonian models describe the zodiacal position of successive events, together with interpolation algorithms for the position between those events, subdivision of the synodic arc. This is quite similar to a Poincaré map describing the normal component of the intersection of a trajectory with the prescribed surface, introduced by Henri Poincaré in modern methods of chaos theory. The outer planets, Mars, Jupiter, and Saturn, move across the sky from being hidden by the sun's beams to their first appearance at sunrise, their first station, that is stationary position, then turn retrograde to their second station, and then again prograde to their last appearance. That may be more correctly called their first day of visibility, hidden by the beams of the sun. The inner planets, Mercury and Venus, move from first appearance in the evening to an evening station to their evening last appearance, followed by the morning first appearance, morning station, and their morning last appearance. In this slide, the picture shows an ideal, noiseless modern simulation of the first return map for Mars' first appearance, assuming that the planet becomes visible at 15 degrees from the Sun in ecliptic longitude, according to the later Greek geometer Autolycus. The positions are simulated from about 747 BCE to 76 CE, the approximate date of the last known astronomical tablet whose colophon has been dated, though recent discoveries revised this to 79 CE. The location was selected to be the East Angular Temple on the Temen Anki ziggurat at a 91-meter elevation, 7 stories of 13 meters, according to a later description by Herodotus. The graph shows a forced oscillation of the successive zodiacal positions of the first appearance, and the invariant curve is approximately a thin line. This circle map has one peak and is almost but not quite sinusoidal. It is not perfectly symmetric. It is called a circle map because it maps angles, position on the circle, into each other. Such mathematical mappings are called unimodal maps, and for continuous mappings, their dynamical characteristics are quite well established. Here is an exemplary family of sine circle maps illustrating forced oscillations close to the border of chaos. An ideal sine circle map of forced oscillations can exhibit chaotic motion for certain ranges of its parameters. There is a devil's staircase in asymptotic average rotation event that is especially clear at the border of chaos. Many people have pushed a child on a swing. One may think that the rate of oscillation would always increase with harder and more frequent pushes. However, there are plateaus at resonant frequencies that are particularly broad are the first resonances denoted by superparticular ratios such as 1/2, 2/3, or 4/3. To connect with Babylonian planetary event models, let us consider the simple empirical model for Jupiter's events denoted by System A1. This exemplary two-zone map shows two zones of constant rotation rate for the event, with linear transitions that preserve periodicity. It's important to emphasize that this does not necessarily imply constant angular velocity for the planet, just for the apparent ecliptic longitude of the event. All the numbers in these mathematical maps are rationals that terminate in base 60 to avoid the accumulation of rounding error that plagues modern simulations of chaotic systems. Here's a possible musical motivation for choosing musical intervals, especially first resonances, to define the levels of angular rate. In particular, the planets move according to discrete elementary steps in each zone. We have later independent evidence that supports the recognition of this concept in antiquity. If we combine this insight with the Greek philosophy we saw on previous slides, we may conclude that the levels of angular rate, or equivalently System A map zones, should be chosen according to a musical scale. In modern chaos theory, particularly the circle map and the standard map, flows are confined to islands of high flux, separated by small regions of low flux, with borders termed separatrices at or near resonances. The next two slides show the musical interval ratios for several Babylonian models of planetary events considered by Asker Arbo. They span the entire musical scale and includes subharmonics, which suggests nonlinearity. The Greek letters denote the planetary events that were considered in the earlier slides. To consider one possible approach to estimating the map parameters, let us suppose that a period has already been determined. The slide shows a family of two-zone maps with equal period. Consider now an exemplary approach to optimization of the map parameters based on closely matching the sequence of zodiacal signs for each event. We can hypothesize that the models are chosen to minimize the number of wrongly predicted signs. To make allowance for the fact that the longitudes were not perfectly known, planets on the cusp are considered to be in the same sign, an orb according to Gray's 2009 thesis. For Jupiter, the first resonances that bracket the simulated data are 4/3 and 6/5. These next two slides show that of these two choices, 6/5 minimizes the number of wrongly predicted signs by comparison with 4/3. So now, let us turn to a classic problem of modern chaos, cardiac arrhythmia, in particular ventricular parasystole, in which a steady heartbeat from the sinus node is perturbed by ectopic beats caused by an ectopic natural pacemaker. Here is a simulation based on a steady beat of 72 beats per minute from the sinus node perturbed by an ectopic beat at 40 beats per minute, such as may originate from the bundle of His. The left plot shows a simulated first return map in phase for the heartbeat, while the right plot shows how the phase evolves with time according to a recent model by Hoppenstedt and Keener. This slide shows an approximation of the time series according to a Babylonian System A type model that uses all the available first-order resonances whose rationals are divisible by 2, 3, or 5. The fundamental rate of rotation per event is 32 degrees and the period is 20/3. That is, the phase angle completes 3 circuits of the circle for every 20 events. This approximation is quite good considering its practical simplicity. Such models are piecewise linear iterated maps in modern terminology. The implications are as follows. Curating records and maintaining protocols over centuries can yield valuable insights. Extant Babylonian System A iterated maps can be described in terms of forced oscillations and their musical resonance. Cultural interaction between scribes and Pythagoreans may have inspired the use of superparticular ratios in Babylonian astronomy. And Babylonian mathematical modeling methods are still useful for solving some complex modern problems easily and efficiently. In particular, nested System A models strongly overlap modern methods of machine learning, including neural nets with piecewise linear activation functions.